Hello and welcome to the lecture of floor and roof span tables. Today what we're going to do is pick up where we left off with footings and foundations and build upon that up to the floor level of an existing building. So today we're going to talk about spans, how far from bearing to bearing certain materials can go, and how we size them appropriately for different types of deflection. So let's get to it. So let's begin by taking a broad view. The structural goal of a house is to safely transfer the building loads through the foundation to the supporting soil. We've talked about this in the previous presentations. Remember when your science teacher said, every action has an opposite and equal reaction? Well, every building load has an equal reaction load. If, when the loads of the house are combined, the house weighs more than the soil can support, the house, as we talked about, will sink. This presentation will focus on how simple beams like joists and rafters react to different loading. As we've learned before, the house acts as a structural system that resists dead loads and live loads. Today we're going to talk about components such as beams, studs, joists, and rafters that act as a structural skeleton that must be strong enough and stiff enough to resist these loads. Strength and stiffness are equally important. For example, first floor ceiling plaster would crack as occupants walked across a second floor bedroom that was framed with a bouncy floor joist. Perhaps the joists were strong enough if they didn't break, but lack of stiffness leads to costly problems. So stiffness of structural members is limited by maximum allowable deflection. In other words, how much a joist or rafter bends under maximum expected load. When we design the beams, the studs, joists, and roof rafters, we need to keep in mind that we only calculate the live loads. Dead loads are not considered in these calculations. So now let's talk a little bit more about deflection. And as you'd expect, deflection is the amount a structural member will bend. And it says here that maximum deflection limits are set by building codes. They're expressed as a fraction. So clear span in inches, which is capital L, over a given number. For example, a floor joist appropriately selected to span 10 feet with an L over 360 limit will have a deflection of no more than 120 inches, which is 10 feet, over 360, which equals 1/3 inches under maximum design load. Drywall attached to the underside of the system is not expected to crack when the floor joist system deflects 1/3 of an inch. Typical deflection limits referenced in code books are usually L360, L240, or L180. These limits are based on live loads and activities experienced in specific rooms of a house. Examples of code prescribed deflection limits and live load values are living room, 360 and 40 pounds per square foot, bedrooms, L360 and 30 PSF, and attic floors, L240 and 10 PSF. And obviously different parts of a building will have different design criteria based upon the number of occupants and the type of use found in that space. This next slide talks about factors of influence. So there are many factors that influence how a system responds to loading. It is important to realize the way you select and use materials will control costs and performance of those components. So first we'll talk about the depth of structural members. So if we look at floor joists, we often see 2x10s used that are spaced 24 inches on center. That's the OC right there. They typically provide a stronger and stiffer floor than a 2x8 of the same grade and species that are spaced 16 inches on center. So 2x10s a little bit further apart can be stronger than a 2x8 closer together. E value, or modulus of elasticity, of the individual elements. So E, capital E, is a ratio that relates the amount of given load that causes a material to deform. A material with a higher E value is stiffer. For example, a number 2 grade Eastern white pine has an E value of 1,100,000, and a number 2 hemlock fir has an E value of 1,300,000. So thereby hem fir is a stiffer material. FB, so capital F lowercase b value, or extreme fiber stress and bending. This is loads caused by beams, joists, and rafters and their ability to bend. FB value, or extreme fiber stress and bending. Loads cause beams, joists, and rafters to bend. As a beam bends, the outermost extreme fibers are compressed along the top edge, and at the same time, fibers stretch along the bottom edge. Those are in tension. The outermost extreme wood fibers on the top and bottom surfaces are stressed more than those fibers in the middle. An FB value indicates design strength for those extreme fibers. The higher the FB, the stronger the wood. Okay, so now with all that information, now we need to know how to apply it. So first we need to do a few things. We need to understand that there's a code book, the International Building Council, the IBC, AF and PA span tables. We'll see the span tables for joists and rafters used quite a bit in this presentation. This will help us determine from bearing location to bearing location what's allowable, the deflection, as well as the FB content. What you see here on your screen is the span tables for joists and rafters, and the link there right beside it would allow you to go to that direct publication. So now it's time to start calculating the loads. For the most part, live load and dead load values for floor and roof systems are considered distributed loads. In other words, the weight is distributed or shared uniformly by the members in the floor or roof system. In order to establish proper sizes, grades, and on-center spacing of joists, you first need to determine what loading is acceptable to the building code. So you'll use your code book here. Look up the allowable loads and deflection limits imposed by your local code. For example, Iowa code book includes the following information. So for floor joists, we see the dwellings, live load and dead load across the top. You'll notice right off the bat, dead load has asterisks in it. And as mentioned before, we really do not do a dead load calculation when calculating the size of members here. So if we look at first floor, we can see a live load of 40 pounds per square foot, a second floor of 30, and uninhabitable attics of 20 pounds per square foot. So now if we take a look at the code book, specifically the code section on load deflection, it states, the deflection of floor and roof assemblies shall not be greater than L360 for plastered construction, L240 for unplastered floors, and L180 for unplastered roof construction. So these are the limits set by the code. We will use these as we go throughout the rest of this activity. You can also use AF and PA's span tables for floor joists and rafters. This is the easiest way to determine allowable dead loads, live loads, and deflection limits. This publication has a much more extensive offering of possible joist and rafter conditions. Once you find the appropriate table in the book, you determine acceptable FB and E values for your particular span condition. Span is a distance from face to face of the bearing locations. For joists, it's typically from the basement side of sill to sill. The loads carried by floor joists, ceiling joists, and rafters are transferred through their endpoints to supporting walls and beams. The ends of these members must be able to react or resist these loads without crushing. AF and PA lists the required compression perpendicular to grain values for joists and rafters for various spans, on-center spacing, and loading conditions in its span tables. AF and PA's design values for joists and rafters lists compression perpendicular to grain values for a variety of species. Just be sure the species design value exceeds the required compression perpendicular to grain value for your structural condition. As we see here in these pictures and diagram, we can see the use of squash blocks. These squash blocks are placed strategically where load is transferred from above through the floor system and down to a foundation or other structure below. As you see in the picture on the left, the person is putting in extra 2x4s that are nailed to the sides of the joists. And the reason for that is, again, to help with that compression force at that bearing location. And the drawings over on the right-hand side also show you where squash blocks are used. In this case, we often see them used on top of the foundation wall at the ends of the floor joists. Okay, so now to summarize the process, we have this checklist here that lists 7 steps. And so let's review that quick. Number 1 says check the plans to determine span and on-center spacing. So these are the design conditions that the architect or designer has laid out for you. After that, number 2 says check the codes for allowable live, snow, and dead load, as well as deflection. 3, select appropriate span table within that code book. 4, match span in table to design condition and determine the minimum FB and E values listed in the span table. It says note, you will have options for on-center spacing and size. So it could be 16 inches on center, it could be 24, or something in between. Number 5, select appropriate species and grade from values listed in the design values table. It says note, you will have the options regarding species and grade, providing you with an economic opportunity. What that means is if it's cheaper to go a 2x6 at closer spacing than a 2x8 at greater spacing, then perhaps it'd be far more economical to go with the 2x6. Number 6, determine required compression perpendicular to grain value in table. So this goes back to whether or not we have to use the squash blocks because of that compression at that bearing location. And number 7, verify that the compression perpendicular to grain design value for the species selected in step 5 meets the required design value determinants. So after learning about this in theory, we are now going to take and practically apply this to an example. Let's now test our skills. So let's work through an example that illustrates the steps involved in using the tables. Let's say you're building a 16-foot addition and have to select the correct size and species of lumber for the floor joists. The joists will be 16 inches on center. Their design span, the exact length from face to face of its supports, is 15 feet 1 inch. And see the illustration below. Even though the overall width of the building, the addition, is 16 feet, if we look closely, we'll see from the edge of bearing to the other side edge of bearing is 15 feet 1 inch. So when sizing joists, use the clear span, the length from support to support, not the full length of the joist. Step 1, check the code. First, check the local code for allowable live load, dead load, and deflection. We see next in figure 2. For this example, I'll use the CABO, Council of American Building Officials, 1 and 2 family dwelling code, which serves as a model for many state and local codes. This sets an allowable first floor live load of 40 PSF and a dead load of 10 PSF, as well as a deflection of L360. So here's figure 2, referenced in the previous slide. And if we look at the schedule below, under use, we go down to dwelling units. It's highlighted there, it says except for sleeping rooms. And we look on the right, under live load, we see it's rated as 40 PSF. So next we're going to consider the allowable deflection. So as before, we'll reference the code book to find out what the allowable deflection of structural members are. If we look down on this where the highlighted area is, we will choose the floors and plastered ceilings for our structural member. And over on the right, we see the allowable deflection for that is L360. The following step talks about the span table itself. And so here we're going to select the appropriate table and span tables for joists and rafters. And I'll show you what that looks like in the next slide. The table of contents indicates that table F2 watches these or talks about these loading conditions. Using table F2, check each lumber size to see if a 16-inch spacing will permit a span of 15 feet 1 inch. We'll start with the 16.0 line in the spacing column at the left of the table, and then we'll take that over to the right until we reach an appropriate span of at least 15 feet 1, which is the distance for our particular example. Then we'll drop down to find the appropriate FB value for the span. And what we'll find is the table will show that 2x8s do not meet the span and spacing requirements, but a 2x10, it will. And it will have an E value of 1.3 million PSI and an FB of 1,093 PSI. And with that, it can span 15 feet 3 inches, more than enough for the 15-foot one. A 2x12 can also do it, with an E value of 800,000 psi and an FB of 790, since that particular member can span 15 feet 10 inches. So let's go take a look at that chart next. As we look at this chart, our first goal was to use a 2x8. I know the print here is small, but I'll kind of read it through for you. So the joist size is on the first column here. The second one is our spacing in inches, so we're going to select 16. And then over here is the modulus of elasticity, and what we want to look at is finding us a number here. See, 10 foot 2 inches the first one, 10.7, 11 foot, and it carries all the way over here with a higher modulus of elasticity, which means more bending. If we look all the way over here, the highest we could get with a 2x8, 16 inches on center spacing, is 14 feet 8 inches. And that's too short. We needed 15 feet 1 inch. So a 2x8, 16 inches on center will not work. So let's take a look at the 2x10 and the 2x12 options next. If we zoom in here a little bit, this chart's expanded now. We can see the 2x10 and the 2x12 listed here. If we go 2x10 and we look at 16 inches on center, which is this one, we see we can span 15 foot 3 with a modulus of elasticity of 1.3, which is allowable. If we look at the 2x12, we see that we can span 15 foot 10 with only 800,000 psi for elasticity. So either one will work. In this case, the 2x12 would be stiffer because the modulus of elasticity is less. Now if we look at the overall stiffness as shown in F sub B, we can see that we have 790 here for the 2x12 and 1093 for the 2x10. For this, we'll use the tables and the design values for joists and rafters. For this example, I've used the relevant sections from tables for hem fir, which is hemlock and fir, two types of wood, Douglas fir and larch, which is another type, and spruce pine fir, sometimes called SPF. We'll see this in figure 4. In the hem fir, either number 1, 2x10, or number 2, 2x12 would work. And remember, number 1 and number 2 refer to the grade of the wood. Number 2 being a construction grade lumber, and number 1 being a higher grade lumber than number 2. So the lower the number, the higher the quality. In spruce, pine, and fir, number 1 using a 2x10 or 2x12 would also do the job. So let's go ahead and take a look at figure 4 now. So looking at figure 4, this is the reference chart that I talked about in the previous slide. And we see under hem fir, which is on the left-hand side of the column, a number 1, 2x10, has a normal duration of 1200 and a modulus of elasticity of 1,500,000. A number 2, 2x12, has a normal duration of 980 and a modulus of elasticity of 1.3 million. Okay, on to step 4. The final step is to make sure the lumber you've chosen meets the required design value for compression perpendicular to the grain. The loads carried by floor joists, ceiling joists, and rafters are transferred through their end points to supporting walls and beams. The ends of these members must be able to resist these loads without crushing. Table 9.1 in span tables for joists and rafters, figure 5 for us, gives us a required compression value of 237 psi for a span of 16 feet, and the bearing length of 1.5 inches. The table permits a bearing length of up to 3.5 inches, but since 1.5 is probably the worst case scenario you'll encounter for joist or rafter bearing, it's a safe value. You can get the compression perpendicular to grain design value for various species selected from the addendum that comes with the design values for joists and rafters. For instance, hem fir has an acceptable value of 405 psi. Spruce, pine, and fir has 425 psi. So as a reminder, when we're talking about bearing, we're talking about what supports the end of the beam. So as you can see in this figure, number 3 is our beam. Number 2 on both sides is what we call our jack stud. And the jack stud, in this case, supports the ends of the beam. Number 1 on both sides is what we call our king stud. And the king stud supports the jack stud and also supports the end of the beam. So in this case, we would say we have bearing on number 2. And since that's a 2x, 2x4, or 2x6, the thickness of that is actually 1.5 inches. So 1.5 inches of bearing is okay for the span we have for this example. We can confirm that 1.5 inches thickness using this table here that shows us the bearing length in inches for the span in feet on the left. So if we look at number 16 on the left and follow that over, we can see we reach the 237, which is more than adequate, with 1.5 inches of bearing. If by chance we needed additional bearing, you see as we go across to the right with 2 inches, 2.5, and 3, the number actually goes down. And that's important for you to understand that the more bearing you have, the less pressure per square inch that you're going to have. Ceiling joists are sized like floor joists, except that deflection limits vary depending on whether the joist will be used for attic storage or will have a plaster or drywall finish. Check your code and follow the AF and PA tables accordingly. When using the tables to size rafters, there are 2 points to keep in mind. First, remember that the rafter span is not the actual length, but its total horizontal projection, as you see in figure 6. Second, use a snow load value for your region in determining which rafter table to use. If your code book says your snow load is 40 pounds per square foot, then you must use a 40 pounds per square foot live load rafter table. The fact that snow loads only act part of the year has been taken into account in the tables, but don't forget to use a snow loading column to get the FB design value. As we conclude, it's important to remember the process of sizing floor joists, rafters, and other structural components is an extremely important skill for designers and construction personnel alike.